Warm good evening to all the participants today in today's bootcamp on single particle model of Felix and Manson. So, in the past, many webinars that have actually been hosted by Decibels before, so we have actually covered the foundations to cell modeling using the approach on equivalent circuit model approach. So quite a lot of webinars have been conducted on that, and so to be honest, like so many versions of the models have been introduced, like 1RC, 2RC, and even PNGV models. So all those content is available for reference. So in this webinar, we will be focusing on the a bit more advanced approach. So like we won't be covering the fundamentals once again, like how we used to do in the past. So this is going to be starting off with a slightly more advanced approach. Where we'll be covering another aspect of modeling and simulating lithium-ion cells, an aspect that is focused on the physics approach or the physics-based approach, and that is called the single particle model. So we will see later on some specific details, what exactly is meant by single particle model, and we'll have a quick comparison of like different types of electrochemical models before we proceed into the details. At the very end, we will also see one of the already like available frameworks of single particle model that is available in MATLAB Simulink itself. So for those who are aware of MATLAB Similinks and development in battery modeling, so the version of 2024 and higher actually gives you the option to use single particle model. That is an electrochemical approach. So we'll have a look into that, and like we can just try to simulate it and see how the results look like in that as well. Okay, so we'll just go through the following topics. So the topics covered for today's bootcamp is that first we'll have a quick overview of what exactly is the difference between equivalent circuit model approach and the electrochemical model approach. So what are the some simple features of each one of them, and which one is the more accurate one, and which one is preferred in real time, things like that. So then we come across the different types of lithium-ion cell electrochemical models. So we will just have a quick overview there. Again, nothing too much in depth. So the idea is not to go deep dive into the the mathematics or the technical part. It's just to get an overview, and then we try to kind of like understand the single particle model, which belongs to the electrochemical model approach. So what exactly is the single particle model? What features it has? What are the mechanisms it includes as a part of the model overview? Then what are the main governing equations? And, as described before, the overview of the Simscape model. So there is already an inbuilt model in Simulink, MATLAB Simulink. So we'll have a quick overview in that. So this is the topics covered for today. So yeah. So as stated earlier, like Decibels Lab has covered a lot of bootcamps and webinars on equivalent circuit models. So where some extensive detail along with cell parameterization, deriving the RC parameters, deriving the voltage equations, and simulating the model for different configurations, such as the internal resistance model, the 1RC or the first order model, 2RC model, and even the PNGV model. So these are the different electrical models, equivalent circuit models that were covered before in the past. So just a quick overview of that. So basically, equivalent circuit models are basically models that are a very simple representation of the electrochemical processes. So instead of going into the electrochemical aspect, what we're doing is we're representing each component inside and each process inside as a set of electrical elements. So like here in the diagram, we're able to see a set of resistors and capacitors and a source voltage and things like that. So basically they represent the resistance and the capacitance of the material inside and of the processes inside. So RS, you can see here, this is basically the resistance known as ohmic resistance, or also you can call this as electrolyte resistance. So this electrolyte resistance is always considered as the series resistance when representing the cell as an electrical circuit. And then the processes, that is the electrochemical processes, they are represented as a set of parallel resistor and capacitor, which you can see named as RP and CP. So this stands for polarization. So basically, polarization is an electrochemical phenomenon that takes place inside the cell. It's a very vast process consisting of many smaller processes. But since you can't represent them so easily in electrical terms, we usually like simplify it down completely into two simple parts, that is a parallel resistor and capacitor. So this entire equivalent circuit concept is built on the theory of Thevenin's theorem. So basically, if you have studied a bit in electrical engineering, you will see that Thevenin's theorem actually talks about simplifying complex electrical circuits into simple electrical circuits. So that's what is the concept of electrical equivalent circuit model. So it's basically all the electrochemical processes and components of the cell are represented as simple electrical elements. Okay, so this is actually a very simple approach and one of the less complex approaches. So like usually you're not considering such complex mathematics in this, where we're considering differential equations or things like, higher order, algebra or things like that. That's not the focus here. So the advantage is this, that it is a very simple approach. It can be used in some simple basic software. You can even have a very simple Excel file itself that does the calculations. And if you want to visualize some results, you can use MATLAB Simulink for this to build a much more detailed model. But there are certain things that this model cannot do. That is, represent some complex phenomenon, like some processes like diffusion or intercalation, things like concentration of ions, or electrode material properties, electrolyte properties, things like that. It cannot represent those. Okay, so that's where the equivalent circuit model kind of falls short. So no matter, you can have like n number of parallel branches, so RPCP, you can have many of them in connection like this. So what you're seeing here is called as a 1RC model. So the reason is that there is one pair of R and C. So like this, you can have n number of RC branches to represent n number of processes inside. But still, there is always a downfall, or there is always a shortage. It's not always able to do justice to the real actual behavior. It can mimic it, or it can simulate it closely, but not completely. Okay. So coming to electrochemical models, so the difference here is that electrochemical models is always physics based. So physical processes are represented here using partial differential equations. Okay, so that is the main difference. So on the left hand side, it is electrical equations like Kirchhoff's law or Kirchhoff's voltage law or current law, things like that. But here on the right hand side, it's completely represented using partial differential equations. So you can either choose your first order or second order partial differential equations based on what kind of model preference you have. And yeah, so you can't use simple things like, or as I told, like Excel or MATLAB, things like that. You have to have a slightly more sophisticated software bench. So basically, your software that you use, it has to be COMSOL or ANSYS, something like this, which is having more sophisticated solvers and things like that. Okay, so basically, this is the quick comparison between equivalent circuit model approach versus electrochemical models. So then, our focus today will be on trying to kind of study the electrochemical models. So what are the types of electrochemical models that we can have? So most commonly in the framework of cell modeling and cell simulation, we can have two types. So one is called as a first order or one dimension model. So that is here, that is the single particle model. So in a short while, we will see exactly why it is called single particle. And there is also another approach which takes it one extra dimension or one degree higher. So second order, it is called as a pseudo two-dimension model. So it is also commonly, in terms of electrochemistry, it is also known as Doyle-Fuller Newman model. Okay, also known as a Newman model. So basically, what is a quick overview of this? So what exactly is the one first order model, or what exactly is the single particle model? So basically, the behavior of ions is considered only in one direction. So like we know that in lithium ion cells, the ions are transferred between cathode, anode, or anode to cathode. So ions will undergo certain processes, and they happen like in like many different directions, actually many different dimensions. So if you take an actual lithium ion cell, it happens in three dimensions, right? So X, Y, and Z. But in case of the one dimension model, we are simplifying it purely to this X direction. So if you consider, you can see here the direction of considering the movement of ions or the behavior of ions. So the redox reactions are considered only in one direction. So that is in the X direction. So ions are either they are moving from cathode to anode, or they're moving from anode to cathode, and only in this direction. That is the X direction. Okay. So if you put it in a geometrically accurate term, it's called radially horizontal. So you can see the markings here. So here you can see that like R positive, R negative. So basically these are all this is R basically stands for the radius, and it basically happens only in the radial direction. It does not happen in the other directions, that is the Y and Z direction. Okay. So that is the feature of the one dimension model. It considers the movement of ions only in the X direction. So coming to the pseudo two dimension model. So basically this is an extension so of the one dimension model. So what it does is that it considers one extra dimension of movement, that is in the Y direction. So you can observe here compared to in the top picture, you can see here. So you have movement in the X direction, and you also have movement in the vertical direction, that is Y direction. Okay. So this the second model actually is very complicated. It involves a lot of variables, and it involves a lot of parameters and equations. So usually, like to simplify this, we many times the first one, that is the one dimension model, is considered. Okay. So our focus will be on this today. So we'll just try to understand some simple mechanics. What are all the mechanisms and mechanics that this one dimension model considers? Despite it being the more simplified version, it can consider some complicated phenomenon. And we'll see some equations as well, like what exactly the equations are. So what is a single particle model? So basically, single particle model. So as explained before, a lithium ion cell is a three-dimensional object, and it considers like it has like many components inside. The anode, cathode, separator, electrolyte, and things like that. So and they're all if you consider the real-time behavior of lithium ion cells, they all happen in 3D, three dimension. So since the cathode and anode are like having some complicated structures and some complicated mechanisms, to simplify this in terms of the numerics and in terms of the equations, in terms of parameters, it is simplified as an individual particle. So you can see that the electrodes are the first assumption here is you can see here the electrodes are considered as single spherical particles. So instead of having a complex three-dimensional structure that allows like three-dimensional movement of ions, we are considering this to be just one big particle. So this one big particle represents the cathode, and the right hand side, the single particle again represents the anode. So each electrode is considered as single particle. Okay, so that's why it is called as a single particle model. And the other assumption, or you can say the simplification, is that the active material particles, they're all considered to be identical in terms of behavior. So if you see the movement of ions within each of these electrodes, the cathode, anode, or the movement between them, they are considered to be identical. So the difference between the anode and cathode is not considered to be such a high extent over here. So that is the understanding of single particle model. It actually simplifies a lot of things instead of like going for higher order equations and parameters, which we have to consider in terms of 3D, which becomes very complex. To make it simpler, we consider it in this approach. And also another simplification that is considered here is that there is some simplification in the electrolyte as well. So apart from the electrodes themselves, there is also a simplification in the electrolyte. So the electrolyte, once again, the complication here comes that there is some like non-linearity in the concentration of ions across the electrolyte also in real time. But in case of the 1D model, we are simplifying it in such a way that the concentration change across the electrolyte is constant. So we are not considering the electrolyte to act as a non-linear element. So everything is linearized here, and many things are simplified. This is what the single particle model does. So this is what is the aspect of single particle model. And here you can see again, RP stands for the radius of the particle. So as described before, we are representing the entire electrode as one single particle. So the particle is considered to have a radius R, and it is in this radius that the ions can diffuse. So they undergo something called as diffusion. So in the next slide, we will see exactly what is meant by diffusion and what is meant by some other electrochemical processes. We will try to understand some of the processes and some of the definitions. Okay. So whenever the processes or behaviors are considered, so one of the most important aspects considered is diffusion. So ions are basically these particles that are transferred between cathode to anode or anode to cathode. And they have a certain diffusion distance, and that distance is considered to be the radius of the particle that we see here, Rp and Rn. So Rp stands for radius of the positive active material, which is the cathode, and Rn stands for radius of the negative active material, which is the anode. Okay. So beneath that, you can see another constant, which is called as N. You can see here N. So this is known as the diffusion constant. So we will again see some equations consisting of this, like what exactly is meant by diffusion constant and all these things. That it comes under the equations, the governing equations. So we'll see it there, right? So this is the overview of some of the features of single particle model. So yeah, so in terms of like the model framework, this is how it is defined. Okay. So along with this, we also need to understand what exactly are the mechanisms that the single particle model can cover, or what exactly can we really include in this. So as I explained before, many of the equations are simplified from 3 dimension to 1 dimension. So all the movement is considered only within the x-axis. So only from anode to cathode, cathode to anode in the x-axis direction. So there are 3 very important mechanisms that are considered in this. So the first one is called diffusion. The second is called ionic intercalation. And the third is the terminal voltage, which is the end product of the cell. So that's the final thing that the cell does. So it produces the terminal voltage. Okay. So diffusion is it's a common chemical phenomenon which you can see in many solutions, whether it could be like liquid solutions or even in solid solutions. You can see that there is movement of particles or movement of ions from any area of very high concentration to area of lower concentration. So this picture over here represents that. So over time, ions naturally tend to move from high concentration to low concentration. So there's a particular phenomenon, there's a particular equation or a law that describes this. It is called as Fick's law of diffusion. We will see it in terms of the equation in the next slide. So what exactly is meant by Fick's law and like why it is considered. Okay, so diffusion is one of the most important principles of electrochemistry. It is basically how ions are shuttled between the electrodes. Then intercalation. Intercalation is basically the process in which basically the ions, when they are transferred between the anode to cathode or cathode to anode, the ions have to sit somewhere, or they have to have a space in which they have to be absorbed. And that space is usually provided within the host material. Okay. So you can see it here. There is a label. It's called as a host. So host material is the material which absorbs the ions. And when it gets absorbed, that process is called intercalation. Okay. So diffusion is the movement. Intercalation is the process in which the ions get absorbed into the material. So basically they have to sit, or they have to get absorbed into the layers of the active material. And that is called intercalation. So intercalation happens on both sides. So cathode also or anode also, it depends upon whether you are charging or discharging. And this is one of the mechanisms that is considered in the single particle model. And yeah, the last one is the terminal voltage. Basically, it considers the potential difference between the anode and the cathode and any ohmic losses present within the electrolyte. Okay, so these are all things which the electrical equivalent circuit model does not cover, as in to say you cannot represent any of these phenomena, because that model, the electrical equivalent circuit model, does not function on differential equations. It functions only on direct linear equations, that is Ohm's law and Kirchhoff's voltage law, things like that. Okay. So yeah, so this is the set of mechanisms that are covered by the single particle model. So these are the main mechanisms. There are some other ones as well, but to give the idea that what are the mechanisms considered, so these are the three main, the most important mechanisms. Okay, and accordingly, we have to also see what are the governing equations. So there are three governing equations based on each of the kinetics that was represented here. So diffusion, intercalation, and the the formation of terminal voltage. Right. So each one follows a law. So as I explained before, Fick's law of diffusion is the main governing law for the diffusion that happens within the cell. Okay. So again, the movement of ions from high concentration to low concentration. So Fick's law of diffusion explains this in a simple way. It talks about the change in ionic concentration is basically proportional to the concentration of ions gradient. So there is something known as a gradient of ion concentration. So it's basically how much ions are present per volume or per area of the electrode material. So if there's a change in the concentration gradient, then there is also a change in the rate of diffusion. So that's basically what this equation talks about. It is represented using these set of differential equations. You can see over here. So you can see that clearly this partial differential equation is a function of two variables, the radius r and time t. Okay, so that makes this a one-dimensional equation. So in two-dimensional equation, you would see that this would be a function of radius r in terms of x and y. Okay, so this equation then expands into a second-order equation where you are having three variables, so x, y, and t. So that is the x direction, y direction, and the time, the variation of time t as well. Okay, so you can see the description of variables. What do the variables within the equations mean? So CS is basically the abbreviation for concentration of ions. So basically, as explained before, concentration of ions is basically how much ions is present, or you can say the amount of ions present within a certain area. So that is represented always as a function of radius r and time t. Okay, so radius, if you recall, this is the radius of the active material, right? So either of the positive or the negative. So the partial derivative of that concentration is basically the gradient. Okay, this is basically what is known as the gradient. So dou Cs by dou T. So that's how we see this. This is the partial derivative. Dou Cs by dou T. This is the total change in concentration with respect to time and radius. So that is known as the gradient of concentration. Okay, so that's what Fick's law of diffusion talks about. Okay, so this is a classic first order partial derivative equation, and they are once again solved with some like initial conditions and boundary conditions. Like some assumptions have to be made that initially like some concentration is there, some initial concentration of ions is present at the surface of the anode, and boundary conditions have to be given, such as how the concentration changes with respect to radius and time. So these equations are dependent on IC and VC. So basically initial conditions and boundary conditions. And then like you can use a mathematical solver to solve this particular equation. Okay. So intercalation is governed by what is known as a Butler-Volmer equation. So this is again a purely electrochemical process, which is as given as an exponential equation here. Okay, so this is an equation that describes the amount of current passing through a unit area, also known as the current flux or current density. So basically, the how much ions is passing through in a certain area. Okay, so this equation is an exponential equation, and only when we solve these two together, we are able to get the final terminal voltage equation, which is once again a function of individual potentials. So we have to find out using some material testing, like what is the potential, open potential of the cathode, the open potential of the anode, and whatever ohmic losses are there within the ohmic resistance that are there within the cell. Okay. So these are the main equations. So diffusion governed by Fick's law, intercalation defined by Butler-Ullmann equation, and terminal voltage, which is basically a more elaborate equation. So it's not just OCV minus internal resistance; it's OCV of each part. That is OCV of cathode, OCV of anode, and the total ohmic losses. Okay, so these are the governing equations. These are the equations that you would find for a single particle model. So actually, it gets much more complex than this. There are many more equations, but to show what the main governing equations are, this gives the brief idea of what are the equations inside. Okay, so now we can take a look at some of the some of the parameters, some of the variables, how they are derived, and like just a quick overview of how the parameters and constants from the past equations are derived. So there is like a lot of material testing that has to be done, and much of this data is reliant on like three types of cell testing. The first one is what is known as a pulse based testing. So where basically you are subjecting the lithium ion cells to multiple pulses, and you can see that listed over here, GITT. Okay, so GITT is a very common type of testing principle that is followed whenever you want to characterize a cell. So GITT stands for galvanostatic intermittent titration technique. There are other words for it as well, HPPC and DCIR. So yeah, they are commonly used to derive the way in which the ions diffuse within the cell. So either you can use this or you can also use EIS, okay, electrochemical impedance spectroscopy. So where you can pass a very small magnitude AC current, and you can observe how much time it takes to diffuse, how much time the ions take to diffuse inside the electrodes. Okay, so this pulse-based testing, or you can use what is called as EIS. These are the methods, the cell testing methods in which many of these parameters are derived. So you can see many variations of this. OCV relaxation, once again, GITT, current interruption. So basically, these are all versions of pulse-based testing and EIS. So different variants and different formats in which you can conduct this to obtain all these parameters. So this is an overview of some of the parameters for single particle model. Like once you understand this set of parameters, how they are derived, we're able to once again go back to the equations and use them for modeling. Okay. So for 2D, it would actually cross more than 50 to 60 parameters. And like that's where actually the 2D model actually loses its advantage, that it becomes very complicated to solve. So that is the advantage of the first order, that is the single particle model. Okay. So now we can take a look quickly at the single particle model that is available in Simulink, Simscape. Okay. So you can see this here. It's already here as a part of 2024A MATLAB and Simulink. So it comes with the package, and you can find this in like the library browser, basically under Simscape elements. Okay, so just have a quick look through on the library browser, and then we can just like go ahead with the like overview of the parameters within the battery single particle. Yep. So we can actually find this under Simscape. And if you go to battery, you can find it under cells. Yeah. So electrochemical, you can find this over here, battery equivalent circuit, table based. So you can find it under these. So single particle model will be available over here. Okay. So in the meantime, let's just have a quick look at the parameters present within this single particle model. So once you find it in the Simscape library browser toolbox, so you can just take a quick look as to what parameters are present within this. So you can actually see here, like what exactly are all the parameters and constants involved in modeling this type of cell. So we begin with the geometry. So here you can define what kind of thickness you want for your anode and cathode, your separator and your electrolyte, and what kind of like geometry in terms of area you can have. So all these constants are pre-entered. So like you can enter them as per your definitions or your requirements. What do you prefer in terms of your preference in terms of your lithium ion cell? So right now, this is configured for an LFP cell, LFP coin cell. So the areas and volumes mentioned entered over here is specific to a coin cell. Okay. So all the electrode properties that you can see over here. So your open circuit potential, I talked about that in the equations. So you can see here like each electrode's potential has been provided here. So each one has been tested separately using a set of testing parameters known as voltammetry. So using that, like they have been like derived over here. So each one's the anodes and the cathodes potential. Then you can see that there is something called as anode maximum ion concentration. So this is basically what I was talking about in terms of boundary conditions. So when I introduced the equations in terms of the fixed law of diffusion, so basically they have to consider like some amount of ion concentration at a particular given time. And for anode and cathode, they're taken separately. So you can see over here. So some by default, some values have been given. So the rest, everything are like electrochemical and chemistry-based parameters like stoichiometry and ratio of some materials and things like that. Even the diffusion coefficients of the anode and cathode have been given here. Okay. So this is in terms of the parameters for electrode properties. So you can find the same thing for electrolyte properties also. So how much basically what properties you would like to include in terms of your electrolyte? It's you can mention that over here. So there is also an option for you to extend it into an electrothermal model where you can like introduce thermal behavior. So you can like even go for like estimating how much temperature or how much heat the cell is giving out. So that option is also there over here. How much thermal mass you want to include for the cell. So there you can like kind of model the heat generation part as well. So these are all the properties available as a part of this battery single particle. And one thing is that right now by default this particular model is configured for a very small amount of current. As in to say the C rate in terms of charging or discharging is not very high. It doesn't it does not allow for very smooth simulation for high currents. So if you want to change that, then you have to change the electrode and electrolyte properties. So namely things like your ion concentration and the stoichiometries, your diffusion coefficients and all these things, you have to change them according to the cell that you're operating or you're simulating, and then go for high current simulation, right? So just for information, this particular cell is being simulated at a DC current of 0.1 amperes. Okay, so again, as I told, this cell is not going to be, right now it is not configured for high C rates of discharge. Okay, so this is basically just a simple Simscape model that is built. Just we are connecting a DC current source to the cell, and we are performing some simple discharge. Okay, so I will just simulate this, and then we'll just have a quick overview of the results. What can we observe in terms of the output? So we can visualize the results in this. So we get a voltage graph in terms of this constant current discharge. So what we have done is a constant current discharge. You can see here, as I had explained before, this has been configured for LFP. So LFP is a type of chemistry known as lithium iron phosphate. So this is a type of lithium ion cell, and you can basically make that out by the flat voltage curve that you can see here. Okay. So in that way, you can actually get a very accurate simulation a very accurate model of a lithium ion cell where you can mimic the voltage patterns with much more accuracy than the equivalent circuit models. In equivalent circuit models, it is not so accurate because we are not including the electrochemical processes like this, right? So this is the kind of results that you can expect once you simulate a single particle model. So again, the thing is that this has been configured for LFP. So if you want to do it for an NMC cell or any other type of cell, the anode open circuit potential and cathode open circuit potential have to be changed over here. So it has to, you have to get it for the anode cathode of an NMC cell. Yeah. So that is the changes that you can expect. When you simulate it for an NMC cell. Yeah. So this is the quick overview of single particle model along with the Simscape overview.